Hello, this is Stuart Mason from Math 156 with script 3C, perm-test-variance.r. And as the title implies, we're still doing permutation tests, but this time, instead of testing if two distributions are centered in the same spot, we're testing if they're spread out the same amount, or if they have the same variance, or what's the likelihood of them having the same variance. So the first way we're going to do this is with an example that uses toy data. So we're going to generate some draws from two different normal distributions using R's rnorm function. Rnorm as in random normal. And as always, if you're curious about this function, you can use the question mark operator to bring up the help documentation. And you see this is actually a member of a family of functions, all involving the normal distribution. So we have rnorm, which is the one we're using for random draws, qnorm as in quantile, p as in probability, and d as in density. So these are all helpful normal distribution functions that give you different values from the normal distribution, and they're very useful for generating confidence intervals or performing hypothesis tests, drawing the density, and we'll actually see another density function later on. But for the time being, let's get back to the task at hand. So run this code. Looks like rnorm expects n, the number of samples we want, the mean, and the standard deviation. So we're saying give us 32 samples, centered at 0 with standard deviation 3, and remember that standard deviation 3 means variance 3 squared or 9. Our second vector is going to be called y. It's 40 draws from a normal distribution, mean 2, variance 4. And so let's take a look at the two sample variances. And you see we got pretty close to 9 and 4, but not exactly 9 and 4, and that's because these are statistics. They're sample variances, and they themselves have variance, so there's some amount of deviation from the center that we expect each of these to have. So we're off by 0.4 here and 0.3 here. Our test statistic is going to be what Paul's calling the F ratio, so we're just going to divide these two sample variances. So now we're going to permute these two data to see if this value of the F ratio is likely for two samples that have the same underlying variance. Before we do that, though, Paul removes the mean from each of these vectors. So we have x0, which is x minus the mean of x, and y0, which is analogous. Now let's just confirm that this is now centered at or very close to 0. So R says negative 7 times 10 to the negative 17. Not quite 0, but very, very close, and that's just the rounding error of the computer, basically. Now the reason we want to do this is because if you have, say x were centered at 0 and y were centered at 10,000, then permuting the two of them and flipping the data back and forth between them would give you a very, very large variance that has nothing to do with the underlying variance of the two samples. So instead we're going to shift them to be in the same place to remove that noise, keeping in mind that shifting a distribution doesn't change its variance. So we haven't altered the variance that we're talking about, we've just moved it to a place where when we start shuffling these samples up, it won't wash out the effect we're looking for. This z vector is just a concatenation of x0 and y0, and we're going to use that to sample from, and now this code should be very familiar by now. So we take an index, which is 32 random draws between 1 and 72, and we put the data on that index and compute a ratio of the resulting variances. And we're going to do this 9,999 times, storing each of the results for later analysis. We can make a histogram of the different statistics we get, and we can add the actual observation we had, and we can compute the resulting p-value, all of this very familiar code. And it looks like, yeah, significant at the 5% level. It's unlikely that these two samples came from distributions with the same variance, which checks out because we know they didn't. Now it turns out that if you're drawing from truly normal distributions, like we were, then the F ratio has a well-understood distribution. It's called the F distribution, and much like the normal distribution, R knows about it. So if we type question mark df, we're going to get the F distribution help function. And you see that one of them is density F. So given a value of the statistic and then two different degrees of freedom measurements, it will tell us the density. And so we can use this function to draw the curve of that distribution. By the way, these degrees of freedom are just one less than the number of samples in either of the two distributions that you're drawing your variances from. So remember, our samples were 32 and 40, so our degrees of freedom are 31 and 39. So we're going to say, okay, draw a curve of this thing for our dummy variable x, which will run along the x-axis. Draw it in blue, and this add equals true argument means don't overwrite the histogram. So let's run that code, and you see we get this, this sort of theoretical distribution that very nicely lines up with our histogram. And then we can even use the sort of built-in pf function with the same degrees of freedom to get the theoretical p-value. And it came out quite close to our permutation test. This is because the assumptions of the f-test that the two distributions are drawing from are normal are very strongly met here because we designed the example that way. If our distributions weren't quite normal, then the robustness of the f-test would be a little bit less good, and the permutation test would sort of be a stronger way to do this, and we'll see examples of the permutation test and f-test disagreeing as we move forward. As Paul points out here, because the f distribution is so well understood, there's actually a var.test function built into R. We can just give it our two data sets, so the x distribution, the y distribution, and the alternative hypothesis that x is greater than y. And so here's just a summary of the test that we ran. There's the p-value. And so basically, at a 95% significance level, we would reject this in favor of the alternative hypothesis that f is greater. Now, as Paul points out, that if instead of permuting the limited amount of data we have, we could sample from the true populations, we'll get an even better fit to the f statistic. And this is true because basically there's only so much information encoded in 72 data points. Shuffling them around can only tell us so much, whereas drawing from the true populations, we can learn a much closer fit to the truth. And you see this curve is going to even better approximate the histogram that we get from sampling the actual distribution. Okay, so let's throw out the toys and bring in some real-world data, and we'll see why the nice, neat classical tests kind of break down. So let's read in beerwings.csv. This should be a familiar data set by now. And we're going to grab all the rows that are men. So we're going to store an index, which beer wings gender == m. Manually split this to get x and y, x being males, y being females. Use the length function to figure out how many men and how many females there were in the sample, 15 each. And we'll compute our F ratio for this data. So it looks like the variance for men is 1.6 times the variance for women. And we're curious to see if it truly is a wider spread for how many hot wings a man eats when he goes out relative to how many a woman eats when she goes out. So once again, we'll take out the sample means before we permute. We'll concatenate the data together. Paul warns that we should use a smaller n on a laptop. I'm on a laptop right now, but I'm pretty confident that I can churn through these. And if it takes a couple minutes, I'll just edit the video. This code, again, should be very similar by now, except he looks like he condensed it a little bit. So instead of storing two different variables, he just directly calls the variance in line on wings index and wings not index. So let's run this. Make a histogram. Throw in our AB line. Check out the p-value. So he says about a 10% chance. I got about 11.5. So maybe not significant. Could be that this is just randomness in our data. Let's compare it with the theoretical F distribution. So now instead of 31, 39, we have 14 and 14 as our degrees of freedom. And you see the classical test really doesn't replicate our results very well. And maybe this is because the assumption that the men and women data are distributed both normally is not very well met. So now we're going to test for equal variance in skewed data. We're going to be revisiting a data set that we know is not very normal, the Verizon data from the previous video. We'll pull out the time vector. And we're going to use the subset function now to grab the times where the group is ILEC. And this drop equals true argument tells R, take this thing that is a data frame and turn it into a vector. Remember, ILEC is the incumbent local exchange carrier. So this is the repair time in hours when the exchange carrier was Verizon. And this analogous one here is going to be the competing local exchange carrier, everything else the same. And this is the repair time in hours, not for Verizon. So this is just some sanity checks here. Paul looks at the lengths and means of each of these, and you can compare them to the textbook to make sure that they are what you expect. Everything looks good. And we can compute our observed ratio. Looks like the variance for the incumbent local exchange carrier is smaller. So they do a tighter job of sort of quality controlling and making sure that their own customers have a similar experience to every other customer. Let's see if that's statistically significant or not. So this code, again, very similar. Paul's gotten a little bit fancier, and instead of hard coding in the length, he has just added the two n variables that we've already computed, and also used it again here to get the size. So let's run this and see what we get. Okay, so this really doesn't look at all like what we've seen so far the F distribution looking like. Let's throw in our observed point and compute the p-value. So Paul doubles this because we have no sort of reason to think that one is bigger than the other going into it. So our alternative hypothesis is just that they're different from one in either direction, which means that it takes a greater difference for us to be convinced. So we double our p-value. So now Paul is going to sort of neatly show us the symmetry of this, but basically he says, well, gee, the small variance of sample 23 is really, we can't be very confident of that, so let's switch the numerator and denominator, put ILEC in the denominator, and now we'll get something bigger than 1, run a similar test, and see if we get a different p-value. But lo and behold, we still get something around 26. And so the reason for that is, you'll recall, the F distribution has 2 degrees of freedom. When we swap them, the result gives us this very cool inverse symmetry, where the area to the left of 1/2 in the df1, df2 case is the same as the area to the right of 2 in the df2, df1 case. I'm having a hard time. This might not be the best medium for me to communicate this without you being able to see me as I talk, but we'll talk about it in class, don't worry. And so we can then draw in the classical F distribution, and you see we get something very different from what our histogram produced, and we also get a p-value that erroneously reports that this is significant. And the reason for this is because the assumptions that power the F-test, namely that the distributions we're dealing with are normal, are very, very heavily violated by the Verizon data, and so the test becomes meaningless. And this is a strong case for the value of the permutation test. Great, so I hope this was helpful, and I'll see you guys on Wednesday. As always, you can send your questions to smason@post.harvard.edu. Thanks for watching.